Hello everyone. This is the absolute last lecture of the software testing course. What I thought I will do in this lecture is to give you an end of the course summary. We'll revisit all that we did in the course, find out what we've not done, and maybe look at some of the tools that will help us to do software testing. If you remember, and if you've listened to all the lectures of the course, towards the end of 9th week, I had done a similar such summary because at that time we had looked at majority test case design and criteria, and I thought it was apt at that time to give a summary through 3/4 of the course. This lecture is essentially a repeat of that summary along with a few additional details that we have covered towards the end of the course. And one of the things that I consciously took a decision of and didn't do in this course is to teach you tools. So what I thought I will do is towards the end of the course, I will give you an overview of about approximately 10 tools that are widely used or believed to be widely used to the extent I could gather information across different firms and institutions that do test their software. So this lecture will essentially be an overview, recap of all that we have done in the course, similar to the one that we did in week 9, along with an overview of software testing tools that are currently being widely used. So again, as I did for week 9, I'm starting with what was committed in the course that we began in the beginning. So this course, we said, will cover algorithms and techniques for test case design by modeling them, the software artifacts through 4 kinds of models: graphs, logical expressions, input sets, and models based on grammars. So then we said these test cases could be applied to test code, white box testing, or could be applied to test based on requirements, preconditions, post-conditions, and invariants, which would be considered as black box testing. So the contents of the course, as I recap from what was posted for you all to see in the NPTEL website, reads as follows. We began the first week by introducing software testing, what are the process levels, the basic terminologies, I clarified a lot on them. Then the bulk of the course, from about the 2nd week till about the 9th week, dealt with techniques and algorithms for basically designing test cases. So we considered software artifacts, which included requirements, design, source code, elements of design like preconditions, postconditions, special models like finite state machines, and so on, and modeled them first using graphs. We learned some graph algorithms for that. We looked at structural coverage criteria purely based on graphs. Then we looked at augmenting the structural coverage criteria with data flow, which is the basis of a course on program analysis also, which talked about definitions and uses of variables. Then we applied the structural coverage criteria and the data flow coverage criteria to graph models derived from source code, from design elements, finite state machines, and from specifications. After this coverage on graphs, we started with logic. I gave you a very, very brief introduction to logic. We saw what predicates were, clauses were, what is propositional logic, how difficult are the algorithms for checking for satisfiability of propositional logic formulae and predicate logic formulae. And then we looked at coverage criteria based on logical expressions. We looked at simple coverage criteria like predicate coverage, clause coverage. Then we also looked at interesting criteria like active clause coverage, 3 versions of it, inactive clause coverage, 2 versions of it. These are widely used for testing safety critical systems. Then we took this logical coverage criteria, first saw how to apply it to source code. If you remember, we saw 2 examples, example of a thermostat, an example that determines the type of a triangle. Then we looked at how to apply logical coverage criteria for design elements, where we looked at preconditions, and how to apply logical coverage criteria for state machines. Moving on, we looked at black box testing. I introduced you to functional testing, as you would find in many popular textbooks. We learned equivalence partitioning, boundary value analysis, decision tables, random testing, and so on. Then we looked at a generic technique that partitions the input domain. and derives test cases by considering combinations of these partitions. We saw how to model the input domain, how to partition the input domain, and we saw about 6 different criteria to model combinations of input domains and write test cases for them. If you remember, we said all combinations coverage, each choice coverage, pairwise coverage, t-wise coverage, and for functional testing based input domain modeling, we looked at base choice coverage and multiple base choice coverage. So that was a break from logic and graph based testing. We did black box input space partitioning based testing. From then on, we moved on and looked at mutation testing, which involved testing based on grammars. I first introduced you to grammars as it occurred in programming languages. To be able to do that, we saw regular expressions, context-free grammars. Then we saw coverage criteria based on syntax, mutation testing coverage criteria. And then what did we say in the course? We said we're going to learn it to test object-oriented applications, web applications, embedded software, GUI, and then we said we'll test symbolic testing and concolic testing. So if you remember, this is how a software development lifecycle works. It's the classical waterfall model. We begin with writing requirements, high-level, system-level requirements, drill down to hardware, software, and specific requirements, follow it up with architecture and design, follow it up with coding and unit testing, and then integration and system-level testing, and then release and maintenance. Testing applies throughout this cycle. And how does testing apply throughout this cycle? We bend the waterfall model to be able to get what is called the V model. Waterfall model is this part. A part of it is depicted on the left-hand side of the V model, as they say. This is just a copy of what was given here. Requirements, architecture, low-level design. I've refined it a bit because I want to be able to link it to integration testing, coding and testing. And what I did in the last phase here was to expand out. Testing comes along with coding, which is unit testing, followed by integration testing, for which inputs or design for test cases come from the low-level design, because that tells you how a software is broken up into components or modules, followed by system testing. For functional system testing, inputs come from the design document. System testing involves putting the entire thing together and testing if the overall software integrated with the system meets its functionality. As we saw in the last lecture, in this week's lecture on non-functional testing, system testing also includes non-functional testing. Non-functional testing tests for various quality attributes like reliability, security, usability, performance, interoperability, and we saw a whole set of non-functional testing attributes. Where does the majority of inputs for designing such test cases come from? They come from the architecture document, which gives a static picture of the various components in the software, how they interact, which is the processor in which it is going to run on, what is the platform features, and so on. After all this is done, finally end users of the software do acceptance testing to check if the software and the system meets its desired requirements or not. In fact, in this week, we saw some testing after the acceptance testing, which is basically going back to the waterfall model, deals with this phase of software development, which is release and maintenance. I gave you an overview of regression testing, which people do when they maintain a software to cater to patches, upgrades, or change requests that happen in the software. So these are the various sets of terminologies that we have seen. Each one tries to attempt testing and classify it into categories based on a particular feature or a phase that the testing is involved in. The 5 types of testing that we saw are unit testing, which is done here by the developer. Especially in agile methodologies, developers are expected to do unit testing. You can't rely and hope that there will be a separate tester who will do it for you. Followed by integration testing. Here components are put together. Components could be software components or software hardware components. We specifically saw integration testing related to software components in this course and not integrating it with hardware. Then system testing is done with the full system in place, software running on the desired hardware platform. Finally, acceptance testing is done by customers, And a related term is beta testing, which is when the software is released but with known bugs, not 100% guarantee that it will cover, and people do beta testing as a version of acceptance testing. So this spans the V model as we saw it. Another classification of testing are what is called methods in testing. Black box and white box. We saw these in detail. Black box testing considers the software or the system as a black box. Only the executable is given. We don't look at its internal details. White box exploits the structure of the considered software to be able to design test cases. Black box is widely practiced across several different testing phases and stages. White box is typically restricted to unit testing, integration testing at software level and at the system level. A lot of the course we did see a mixture of white box and black box testing as it applies to the first row here. We didn't spend too much time for black box testing as it applies to the second row here. The last week in this lecture, I gave you an overview of some of these techniques. Another related thing is what are the activities or the processes of testing. The first thing is, after you have your testing goals, is to be able to design your test cases. That's what we did most of the course. We did an algorithmic style of designing the test cases. And then once you design a test case, you pick your tool of choice for execution. For this course, I had introduced you all to the tool JUnit because it is popularly used for Java. And the book that I followed for majority of the course also uses JUnit test cases. So that's why I had introduced that tool to you. I hope you were able to try out some examples with JUnit. Once you have JUnit and you figure out how to automate your test script on JUnit, the next job is to execute it and evaluate the test case to see if the test case has actually revealed an error in the program or not. Typically, a lot of other activities happen along with testing. Test management, test maintenance, documenting the test cases. Typically, these activities have become very important after a software is released, when it is being maintained here, because that's when you do regression testing as we saw in this week, and the sources, documents that are needed for regression testing are the documents that you keep with the goal of test maintenance, which is basically reusing a set of test cases for regression testing, and documentation, which talks about documenting a test cases, which will help you to select which test cases to reuse for regression testing. Then this is a summary of the criteria-based design that we saw. I just repeated to you, so I'll be brief here. Software artifacts could be code, source code, design, preconditions, postconditions, assertions, specifications, models like finite state machines, activity diagrams, and so on. I take them based on what I want to test. I can model it as a graph, model it as a logical predicate, consider only the inputs that go into the software artifact, or work with the syntax of the artifact. Once I model the software artifact using one of these four, I can use it to test source code, design, finite state machines. I can again use it to test source code, finite state machine, and specifications. But when I consider input space partitioning, it's only black box. So I can use it only to test a software with reference to its black box testing. This was the main bulk of the course as I taught you from the book by Amman and Ofut. Along with this, we also saw several classical software testing terminologies. Typically, when you pick up other books in software testing, when it comes to testing source code, you would hear of terminologies like cyclomatic complexity, independent paths, basis path testing, D-to-D paths, statement coverage, branch coverage, loop coverage, path coverage, and so on. We did look at all these terms because these are classical standard terms in software testing. Now, I hope it is clear how these terms relate to the coverage criteria that we saw in the course. Then when it comes to design integration testing, I told you about top-down integration, bottom-up integration, the various kinds of interfaces, message passing interface, client-server interface, shared variable communication. Then we saw what test stubs and test drivers were, how to create stubs, how to test using stubs and drivers, and typically do top-down or bottom-up integration, which are the two most popular integration testing techniques. In black box testing techniques, I did a module on functional testing where you learned about equivalence partitioning, boundary value analysis, and decision tables. In the process, we also learned a bit of discrete maths and formal languages. I taught you graphs, graph algorithms, DFS, BFS, topological stored, strongly connected components. Then we looked at logic, specifically propositional logic and basics of predicate logic. How difficult is the satisfiability problem? For propositional logic, it's NP complete. For predicate logic, it's undecidable. So we work with a lot of heuristics bundled together as SAT solvers to be able to solve the logical formulae. We also saw a detailed introduction to finite state machines, to regular expressions, to context-free grammars, as they were used to build grammars or the syntax of programming languages. So we saw several examples of source code. If you try to recap the examples that we saw throughout the program, we saw triangle types, then we saw thermostat, several different examples. Then we saw examples of sequencing constraints, preconditions, postconditions. If you remember, calendar method, queue example, file open, file close. Then we saw examples of finite state machines for specifications, subway, microwave oven, and so on. So we also, after week 9, this was what I did newly after week 9. A lot of what I told you now was a repeat of the overview that I had given at the end of week 9. After week 9, we mainly concentrated on the following topics. We saw how to test web applications, static hypertext websites, dynamic hypertext websites from the client side and from the server side. I had taught you one technique each for server side testing and for client side testing: bypass testing, user session database testing, and testing based on graph models which were derived from the code corresponding to server as atomic sessions. And then we also looked at testing of object-oriented software, because typically object-oriented software have a lot of features like inheritance, polymorphism. We did a sort of a crash introduction to all these object-oriented features. We saw how these features can lead to lesser static determinism, and you don't know which version of the variable is being called and how to determine the state. We saw the models of yo-yo graphs. We saw various object-oriented faults in detail. And towards the end, in this week, I defined object-oriented integration testing coverage criteria for you all. Last week, week 11, we saw symbolic and concolic testing techniques, which was a distinct departure from the coverage criteria-based techniques that we have seen till now. In concolic testing, we particularly saw the Dart tools algorithm. Then, as requested by the users of this course, I gave an overview of these topics: mobile applications testing, testing non-functional things with specific focus on performance testing, and regression testing. While I did this, I also gave you references to some tools, open source and proprietary, that you could have access to or use it to try it out. And what we didn't do in the course. What else is there in software testing that we didn't do in the course? First of all, I hope you do believe that we have covered a lot in the course, and I hope it was useful learning for you. But because like any other course in any other topic, we have to leave out a lot of things. So what we didn't do is non-functional testing in detail. I did one module on non-functional testing. We covered performance testing a bit, load, stress testing. But security testing is a very beautiful, theoretically rich area which we didn't cover at all. Then there is something called reliability analysis, which I told you when we did non-functional testing. Typically, reliability analysis for both software and hardware work with models that involve probability, like discrete Markov decision processes, hidden Markov models, and they need a good amount of statistics and probability to be able to determine the reliability, right, which talks about measuring parameters like mean time between failures, average downtime, average uptime, and so on. We didn't do any of those because those are quite involved theoretically and algorithmically and need you to pick up that kind of maths. Another big area in testing which we have altogether completely left out is usability testing. Usability engineering itself is a big area. Inside that, testing for usability is very important, catching up a lot because of all the apps and games and other interfaces that we are dependent on to use our software. specific part of usability testing is testing of graphics user interface, which I did list as a part of the contents of the course, but I didn't do because of lack of time. There is a particular style of techniques by which you work with graph models that look a lot like finite state automata, using which you can test graphics user interface, which I didn't do. Testing of embedded software is very critical because typically embedded software is a safety critical system and it goes through very rigorous testing process. So I should say that all the coverage criteria based testing that we did so far can very well be used to test embedded software for GUI applications and so on. But specifically for things like embedded software, people do what is called real-time testing also, because such software come with a lot of real-time constraints like interrupts, timeouts, and exception handling features. So though there is specifically a lot of testing done for these kind of software, which we didn't look at. But whatever we looked at can be applied to test embedded software and can also be applied to test GUIs also. And tools, I had introduced you to JUnit mainly because the programs that we dealt with were all compatible with JUnit. It's a nice open source testing tool for Java thing. But apart from JUnit, we didn't do any other tools. I will do some tools now as a part of this lecture, give an overview of several other tools. And the other thing that we didn't do, if you go back to the V model here, after system testing comes acceptance testing, which is a software is released in the market and users basically check if a software is working or not. There is not much algorithmic content in that thing. Typically, for an acceptance testing like a car, what they do is to see if the brakes of the automatic braking system is working fine. They try to crash a car and check the brake system. Similarly, for the software that controls how the airbags are handled, they try to create a scenario to check if the car controller is bringing up the airbags properly or not. So these things are either done using exhaustive simulation setups or in the real life. So there is not much algorithmic mathematical content that can be taught as a part of such a course. So we didn't do acceptance testing because of that reason. So now for the rest of this lecture, I want to spend some more times on looking at tools. Before we do that, I want to justify and tell you why we didn't look at tools at all throughout this course. It might be a very natural question that you have. Tools are needed for testing. They are indispensable, in fact, for testing. Testing cannot exist without automation with the help of tools. Automation is necessary only for executing a test case, for documenting a test case, and maybe use the results for analyzing the test case to see if there is an error in the software or not. But who is going to design the test cases? That has to be done by the tester or a programmer. That's what this course focused on, algorithms and techniques for test case design. That is manually done. Once that is done, you should be able to use any tool for automation and to be able to execute it. Also, the other reason why I didn't really teach tools is basically what does teaching a tool mean? You download the tool, you learn its interface, you learn the commands of the tool, or if it has a web interface, you learn the web interface or the IDE. So basically all our focus will go on figuring out the tool and trying to learn its interface and how it interacts with the user. I'm sure you would agree with me that that can be picked up on your own and you really don't need a teacher to be able to teach you with that. So typically in a classroom course, we don't focus on tools. It's only if you have a lab component attached to the classroom course that you would do the tool, and that also you sort of try to pick up on your own. We typically don't teach it as a part of the routine lectures. So what I'll do for the rest of this course, this lecture, is to give you an overview of tools. So tools that are involved in testing can be broadly classified into the following categories. Tools that do functional testing automation, tools that do non-functional testing, typically load testing, performance testing, security, vulnerability analysis, and tools that are used for test management, which is basically to archive, record a test case, to track the progress of testing, to plan your testing. Project managers who focus on testing project managers use these tools. Another important category of tools are what are called bug tracking tools. You might have heard of tools like Jira and all that. Once you do a defect, right, find a defect using testing, the idea is to be able to record that defect, take it back to the developers, see if the developer is able to fix that bug or defect, retest it again to see if the defect has been mitigated. So once you find a bug or a defect, it needs to be tracked from the time it was found to the time that it is rectified. So there are specific tools that help you to track these bugs or defects. Those are called bug tracking tools. As a part of my modules on various non-functional testing, I had given you some of the non-functional testing tools that are popular. And please remember, when we did that web testing, I had given you the most exhaustive web page that I am aware of that contains several different non-functional testing tools. So what I'll do now, and I also gave you tools for regression testing and mobile apps testing that I'm familiar with. What I'll do now is I'll try to focus on testing tools that will do functional testing. Some of them will also test for load and performance. We'll see them as we go on. Here is what is believed to be the most widely used set of tools for test automation. Selenium, Water, this is pronounced Water, tool called Ranorex, which I already introduced you this week in another module, testing Whiz. Then there's something called HPE-UFT. This tool was recently renamed. It was popularly known as QTP. You might have heard about it. There's another tool called Sahi. Sahi and Selenium are used by many companies. Test Complete, Telerik TestStudio, What-In, which was motivated by Water. So we'll just look at a few of these tools and see what they can do. So Selenium is basically a suite of tools to automate web browser. It's web browser based test automation. So it automates web browsers across several different platforms, Windows based, Linux based, and so on. Selenium, as I told you, runs on many different browsers, many different operating systems, can be controlled by several programming languages and testing frameworks. It basically gives you a web interface to handle and automate your test execution. It offers record and playback features, which I told you in the context of regression testing, to write tests without learning the IDE, and it is considered to be one of the most used tools in the industry. Then there is a tool called Water, pronounce it as Water. It stands for Web Application Testing in Ruby. Ruby is this programming language. It basically is an open source family of libraries that are written in Ruby, again for web browser automation, for automating web browser automation and text execution through web browser automation. A Water project typically consists of smaller pieces. Water Classic is an IE process where the server is the IE process, and what does it serve? The clients, they are the objects that you want to automate and execute as a part of your test case execution. How does it do? It exposes their methods, and then the Ruby program in which Water is written becomes the client and it manipulates the automation objects. So that's how the classical version works. There is a web driver Water, which is a modern version of Water API based on Selenium 2. So Selenium can be integrated with Water. Then there is something called Water Spec, which is basically an executable version of the Water API. Then another popular tool is testing Whiz. It's a codeless automation testing tool for software testing, web applications testing, mobile apps testing, testing for databases like SQL, cloud testing, testing by hosting your thing on the cloud, web services which form a specific part of web apps, and for API testing. The nice thing about testing Whiz is that it's integrated with several different bug tracking and test management tools. So you could actually use the same tool to be able to track your defect if you found any and manage it later instead of switching over to a separate bug tracking tool. And because of this, testing Whiz, the belief is that it's considered good for people who follow agile methodologies. The next one is QTP. Earlier it was known as QTP, short form for Quick Test Professional, but now it is called HPE Unified Function Tester. It's primarily used for functional testing, regression testing, and testing of service apps. You can automate user actions on a web browser. This is what always happens in most of the automation tools. Or you can automate it on a client-based computer application that you write for it. You can test the same actions for different users, for different data sets on various Windows operating systems and various browsers. The next popular tool in our list is Sahi. The nice thing about it is that it's an open source tool, again for test automation. It automates web application testing. You can use it with several different browsers. It supports all these frameworks that are listed here, and it also does record and playback like most other automation tools do. Telerik TestStudio is the next in our list. This again automates desktop, web, and can be used for mobile applications testing. I don't think I listed it in my mobile applications lecture, but I'm not sure. This also does non-functional testing. It can test for graphical user interface, load, stress, and performance. It supports many programming languages like HTML, Ajax, ASP.NET, JavaScript, and so on. It offers record and playback features. In fact, most of these tools offers record and playback features, supports several browsers, can do manual testing, and it's integrated with bug tracking tools. So this was an overview. I didn't give URLs because I realized that they keep changing, and once I give a URL for such a long list, it is going to be difficult for me to keep track of when the website gets updated. But feel free to Google for them. You will be able to get the URLs well. So this will give you a basic set of test tools, open source and proprietary ones, that are available for free trials for you to start your testing exercise if you are interested. If you want to call yourself as an expert, complete expert in software testing, apart from this course, you could also learn one of the popular tools like Selenium or Sahi or one of those, and get to familiarize yourself with their interfaces and what their capabilities are and how to do automation of test case execution in them. That will definitely help you if you're interested specifically in job interviews and so on, to be able to get a job as a quality expert. So I hope you enjoyed this course, and we hope these set of lectures were useful for you and you learned a bit in software testing. All the best for your upcoming exams. Hope to see you all again in NPTEL sometime. Thank you.